Okay, so I'll get started. So we've had a few talks today talking about different platforms to realize topological flat bands and searching for fractional churn insulators. And so one question that you might ask is, well, how can we find new materials that are going to realize these different phases? And in order to do that, we need to have an efficient way to search the vast material parameter space besides doing full-blown superlattice calculations. And so that's what the goal of our work is, to have a efficient way to quickly determine whether, if we're given some material that we have some continuum model and we impose a superlattice on it, are we going to get a topological flat band? In order to develop such a kind of heuristic type of criteria, we need to give up something. And the thing that we're giving up is that we're going to assume that the superlattice is perturbative. So this is a very kind of simplified route, but from this simple idea, we can also get some simple intuitions that come out. And then finally, we can actually generalize our results to these anomalous systems where the flat band is actually generated by interactions. So I'm actually thinking beyond Moiré. I'm thinking about superlattice band engineering. And so there's a few different routes by which we can generate superlattices. So one would be this first line where I show different routes towards nanopatterning, so dielectric patterning or patterning different graphite gates, where the superlattice is actually very much engineered. The second approach would be Moiré hetero-bilayers. So if the two layers are different, you might model them by one layer imposing a superlattice on the other layer. And I just wanted to highlight this idea in the TMD hetero-bilayers, which I'm not going to talk about, but I wanted to give a shout out to Daniela Guerci, who's a great postdoc I've been working with at Flatiron Institute, who's floating around somewhere here, and would be happy to talk to you about these different ideas in the TMDs. And then finally, the other route, which the conference organizers put this all in a great order for me, is that we can also have spontaneous symmetry spontaneous symmetry breaking, where the Hartree-Fock interactions generate the superlattice potential. So these are all different routes by which we can get a superlattice, and they're not necessarily limited to Moiré platforms. Okay, and to kind of state the obvious, superlattices generally give flat bands, but here we're interested in topological flat bands. And what do I mean by topological? Specifically in this talk, we're talking about bands with a churn number, but this platform could be generalized to other types of topology. And so why do we like these churn bands? Well, they can exhibit the anomalous Hall effect and hopefully give us this interesting fractional churn insulator phase. So I'm going to give two examples that I'll be coming back to of these topological superlattice bands. So the first is something that my group has been working on for a couple of years, which is bilayer graphene subject to a spatially modulated potential. So the experimental setup is shown here. So the basic idea is that you have Bernal stacked bilayer graphene, and then you have one of these pattern gates where maybe you punched holes in the gate in a periodic way. And so then if you put a voltage on that gate, then the graphene will feel some spatially modulated potential. And if you also have top and bottom gates, then you can also get a displacement field. And so this is, again, a very tunable platform. And we showed that this platform gives us topological flat bands. There's a nice intuition for where these topological flat bands come from, which is if we just take a very simple model of bilayer graphene, we get this familiar dispersion. If we add a displacement field, the displacement field opens up a gap, and we get valley churn bands where the Berry curvature is pretty tightly concentrated near this gap. And so the role of the superlattice here is to take the regions of the band structure where the Berry curvature is concentrated and open up gaps so that we now have flat bands. So in other words, the displacement field already gave us topological bands, and the superlattice gives us flat bands by making this kind of mini Brillouin zone. So this is a simple toy model picture, and it's backed up by some superlattice calculations that we've done. So this is one sample band structure for some pretty realistic parameters. This is an experiment. The parameters are done from an experiment at Stony Brook where the periodicity is 50 nanometers. So that's a really large periodicity compared to the Moiré periodicity. And so our bandwidths can be really small. So you can see these flat bands have a bandwidth on the order of like 1 MeV. And we see that there's a really flat churn band. And the other thing we can see is that there's also some interesting bands up here in this kind of spectrum. So we have a churn 2 band, but it's separated by a really small gap to the other bands. So mostly I'm going to just be interested in these flat and isolated bands. One of them has a churn 1, and the other is a churn 0 band, a trivial band. The other platform has already been introduced, which is this rhombohedral graphene with aligned HBN. And so integer fractional churn insulators have been realized here. And the puzzle, which has already been addressed, is that some of these states are realized when the displacement field is pushing electrons away from the Moiré potential induced by the HBN. And so as the last talk kind of put forwards, but has been recognized by several other people, one resolution to this puzzle is that I think the resolution is that the Hartree-Fock interactions are very important for realizing the superlattice. And so in other words, if we stick to this single particle band picture and consider the potential induced by HBN, then we kind of get this mess of bands which has no gap. And now you consider Hartree-Fock interactions and you get this isolated churn band. And this was discussed extensively in these papers here. And I took this figure from this paper, which I think is also going to be the subject of the next talk. Okay, so that's a little bit, those are some of the types of platforms that we're thinking of. So the question which I posed in the beginning is, well, how can we actually predict these platforms? Usually what we have to do is we have to compute the entire band structure with the superlattice. And this can be a bit of a computationally intensive calculation. The superlattice is big, there's lots of bands. And then we need to compute the churn number. The churn number is an integral of the Berry curvature over the Bruin zone. That's also kind of an annoying calculation. So this is a bit of a long-winded process. And so the goal of this talk is to present a unified framework using symmetry indicators by which we can predict band topology from simple inputs. So if our original band is, say, bilayer graphene, and we know the Berry curvature, or we know the quantum geometry of that band, can I bypass these steps 1 and 2 and find a heuristic to figure out, like, what's the amount of Berry curvature that I would need in order to realize a topological flat band in some superlattice potential? So that's what we're trying to do. We want to take simple inputs like Berry phase, or what we call form factors that capture the quantum geometry of the band, and then we impose some kind of superlattice, and it can have harmonics that have a sign or a phase. These are the inputs that we want, and we want to output the churn number of the lowest superlattice band without actually doing a calculation like this. And as I said before, the assumption that we need to make in order to make this work is that the superlattice potential can be treated perturbatively. That's kind of the ingredient that we need to make this simplification. Okay, so we're going to rely on what are called symmetry indicators. So I wanted to make one slide review on symmetry indicators. What these are is a shortcut to finding churn number. So instead of integrating Berry curvature over the Bruin zone, we can just look at the high symmetry points, look at the symmetry of the block bands, and figure out the churn number. And so I just want to show a quick example of how this works for people who are not familiar. One way to think about this is, suppose I have a topologically trivial band. That trivial band has localized Wannier functions. Those localized Wannier functions can sit at some certain positions in the unit cell. And so I can enumerate them. And so I can make a list. I've made a list of them here, which is in some kind of coded language. But basically, ABCD tells me where the Wannier function is localized. S and P tells me about the symmetry of the orbital. And with this data, I can look at high symmetry points in the Bruin zone, and I can check whether, say, a C2 symmetry has a positive or negative eigenvalue. So I enumerate this list, and the thing that you notice is that in each one of these rows, there's either all pluses, all minuses, or 2 pluses and 2 minuses. It's always an even number. So that means that whenever you have an odd number of plus or minus eigenvalues, that you're not in one of these kind of trivial types of bands, and so you have to have a churn number. And so using the C2 symmetry eigenvalues, you can get the churn number mod 2. And this is a lot simpler than integrating Berry curvature over the Bruin zone. So this was kind of, several years ago, we kind of generalize this to all different space groups, but we actually don't need all of that technology for this talk. The technology that we need was actually developed just much earlier than that, which is the symmetry indicators for Chern number with discrete rotational symmetry. So if you have 3-fold, 4-fold, or 6-fold symmetry, you can get the Chern number mod 3, 4, or 6. And these formulas are actually quite simple. So basically, each one will have an ingredient. The ingredients will be, what is the symmetry eigenvalue at a high symmetry point? That's what's on the right-hand side. That's what these lambdas are, symmetry eigenvalues at high symmetry points. And then the left-hand side just gives me the Chern number. So they're very simple, simple ways to compute the Chern number in the presence of symmetry. Okay, so how can we apply this to the problem at hand? Well, I outlined this traditional route to finding the topology of a band. So now we can simplify it. We don't need to compute the whole band structure. We only need the block eigenstates at high symmetry points. And we don't actually need to compute the Chern number directly. We only need to multiply the symmetry eigenvalues. So this is a great simplification that's been known for, for the past decade. But even to exploit this, we still need our superlattice band structure because we still need the block wave functions at the high symmetry points in order to use the symmetry indicators. So the next advance that I'm going to promote is that if we treat the superlattice as a perturbation, we don't actually need to compute the superlattice band structure. We only need to use simple data from our original non-superlattice band, and from that simple data, we can get at the Chern number. So how do we do this? I'm going to just kind of try to sketch how this works. So this is basically like the nearly free electron model, textbook level stuff that you might remember from Introduction to Condensed Matter Physics. So you have some continuum model for your band. In the nearly free electron model, it's just a p²/2m, but in our case, it will be like bilayer graphene with a displacement field. You impose your superlattice, so your superlattice has some real space form and then it has some harmonics. And what the harmonics do is they couple different points in your, for your underlying continuum model. And so they define a Bruin zone where you didn't have one before. So they define the high symmetry points. And so if you're treating this perturbatively, you can write a Hamiltonian in this kind of degenerate subspace of high symmetry points. So you'll have on the diagonal, you'll just have some identity matrix because all of these high symmetry points they'll be at the same energy because we're assuming that you have symmetry. And then on the off diagonal, you'll have the harmonics of this potential. So in this 1D case, you just have two high symmetry points. This would just be a 2x2 matrix. And then the off diagonal would be whatever your superlattice harmonics are. Now, in our case, this is not the nearly free electron model. This is some more complicated continuum model, like, say, bilayer graphene. So these off-diagonal elements, they don't just have the superlattice harmonic, but they also include these form factors. So the form factors tell you how much does a block eigenstate at some high symmetry point overlap with the block eigenstate at another high symmetry point. In your nearly free electron model, you have no choice about that. But in these, in the types of models that we're thinking about, like in graphene states, the block eigenstates are obviously going to wind around in the Bruin zone, so we need to know about their overlap. And their overlap is captured by what we call these form factors here. And so these form factors will enter into this matrix. Now, this is a very simple type of matrix, and so we can get, remember what we need for this to use these symmetry indicators is we need the symmetry eigenvalue of these block bands. And so we have this 4x4 matrix. We can easily diagonalize it, but we don't know which eigenvalues will go into the lowest band. So what will happen is that there'll be some mini band that splits off. That will be the lowest band, and then there'll be some next band, and the superlattice impose all of these different bands. And we need to know what are the symmetry eigenvalues inside of the lowest band. And so we can actually find this in closed form for matrices that are so simple. And so the eigenvalue just takes some form. So if we have a p-fold symmetry, the eigenvalue is always going to be some multiple of e to the 2 pi I over p, and we just need to figure out what this exponent is. And I'm not going to show how we did that, but it takes some form. The round down function comes from, well, we're trying to find the lowest eigenvalue. and what enters is this kind of phase here, and the phase is exactly coming from these off-diagonal elements. So like I said, the off-diagonal elements include a superlattice harmonic and a form factor, and these are exactly the things that are appearing here. So if you know those details from your original band, you feed them into this formula, and you can find the symmetry eigenvalue of your lowest superlattice mini band. Then we can just plug into this Chern number formula, and we have the Chern number of this lowest mini band. And so maybe this seems kind of complicated. Maybe I've introduced too much complication for the end of the day. But the basic point is right here. We have a formula for Chern number. The left-hand side is Chern number, and it's coming from simple data of our continuum model. We don't need to compute the superlattice band structure. What's that simple data? The simple data is that we have a symmetry eigenvalue, which is expressed in terms of the superlattice harmonic and these form factors. Those are just something that we can easily compute from our continuum model. And then there's some integer that goes in front, and these integers are worked out. That's part of that's not complicated. So that's the advance here. We can get the Chern number only from our original band, and we never compute the superlattice band structure. If we have a long period, we can actually recast this in an even more elegant way in terms of Berry curvature. And so now, I said we need these form factors. We actually don't need form factors. We just need Berry curvature. And so this is actually kind of the point that was mentioned in the previous talk. If your mini Bruin zone encloses a certain amount of Berry curvature, then you will automatically get a Chern band. And if it doesn't enclose enough, then you won't get a Chern band. And that's exactly the thing that we've quantified here. And so maybe I don't need to go through all the formalism, but yeah, that's what the main point is. If you give me your superlattice, you tell me how big it is, that imposes a mini Bruin zone on my continuum model. That mini Bruin zone encloses a certain amount of Berry curvature, and if the Berry curvature reaches a critical amount, then that will automatically be a Chern band. Right, this is the point that I just said. Berry curvature is essential to realize the Chern band. If you don't have any, then hope is lost. And so the main result of our work is a table like this. So let me just show you what this table means. So these are the different symmetry possibilities. So let's just focus on one column. Let's just suppose that we have threefold rotation symmetry. Then the main result would be, okay, actually let's do the fourfold. This is even simpler. In this long period limit, the Chern number is given by the simple formula. Phi b is the Berry curvature enclosed in the mini Bruin zone. And so you can see if that number is 0, I just round down and I get 0. I have 0 Chern number. And that Berry curvature needs to reach a critical number, which in this case is pi, in order to give me a Chern number to that band. So these other columns are very similar. It's a very simple formula based on the Berry curvature enclosed in the mini Bruin zone that gives me the Chern number of that band. If the superlattice is not big enough, we can't make a simplification like that. And so then we need to look at the last row of this table, which is saying the point that I made, which is kind of the formula I showed before. You don't just use Berry curvature, you use these quantum geometry form factors. They're also easy to compute, and we get these kind of, this is actually a phase diagram where each color means a different Chern number. And so actually if we have completely trivial quantum geometry, that would be like a free electron model. That's sitting at this point in the phase diagram, we have 0 Chern number. We have to have a critical amount, the form factors need to reach critical values in order to get a Chern number in either direction of this phase diagram. So that's the main result of our work. So I want to show how this works in a couple of examples. So now I'll circle back to the examples I showed earlier. If we have bilayer graphene in a superlattice potential, we can look at our table. We'll look at the column that says n equals 3, and then we have this very simple formula for the Chern number. It has two input data. One is the superlattice harmonic phase, and the other is the Berry curvature enclosed. In bilayer graphene, the Berry curvature is determined by the displacement field. However strong your displacement field is, it tells you how the Berry curvature is concentrated. And then you have some superlattice potential, which say has a plus sign or a minus sign, so that determines the phase of the harmonics. And so the band structure that I showed before is sitting in this region of the phase diagram, so it gives me a Chern 1 band. If I wanted to look at the other valley, I could think of that as switching the sign of the displacement field. That would give me a Chern -1. And if I wanted to answer the question of, well, why do I get a Chern 1 band instead of a Chern 0 band, I can actually swap the sign of both the V naught, which is the displacement field, and the superlattice field. And that gives me a particle hole symmetry, and that would take me from the Chern 1 band to the Chern 0 band. So all the features that I see here, which is I have a Chern 1 band and a Chern 0 band in one valley, and the other valley is opposite, are capturing these different regions of the phase diagram, which come out of that formula in the table that I showed. So this is kind of how it agrees with our band structure calculations. So the next question would be, well, how can we do this? What do we need to do to include these anomalous crystals where the potential is generated by the Hartree-Fock interaction? And so here our goal is, you give me a periodicity, say the periodicity which is set by aligned HBN on, say, pentalayer graphene. You give me a periodicity and you guess at the Chern number. And then because it's Hartree-Fock, we're going to make a self-consistent solution, and we're going to see whether their self-consistent solution exists for an isolated band with that periodicity and that Chern number. That's what our goal is. And we need to make this approximation. This is kind of similar to the 3-patch model in the previous talk. The way this approximation works is that we need to assume that these kinds of expectation values that are going to come up in the Hartree-Fock theory are only non-zero if these points are high symmetry points. And so that's basically the same thing as saying that the potential we generate can be treated perturbatively, and we only need to look at how it opens gaps nearby the high symmetry points. Okay, so under these assumptions, what happens is that we can take exactly the previous table that we made, and we can replace the superlattice potential, which had these harmonics, with the Hartree-Fock, whatever the induced Hartree-Fock potential is. So I showed some formula like this before, and now this is the same formula, except I wrote Hartree-Fock up here. Okay, what's the problem? Well, the problem is that this looks simple, but it's not a closed form. It's a self-consistent equation. And so basically, what feeds into the Hartree-Fock potential is these Fourier transform density operators, but what feeds into the density operators is the symmetry eigenvalue. And so this is some kind of loop. And you can solve this loop because there's just some kind of small number of equations that you need. But actually, Valentin made some pretty clever advance, which is if we rearrange all these equations, then we actually only need to solve one equation instead of making a loop. So in other words, we guess at the Chern number, we guess at the periodicity, we compute this quantity on the inside, and then we do this round down function and see if it's 0. And when we do this, if the answer is yes, that means we have a self-consistent Hartree-Fock solution with the Chern number that we guessed. If you round down and you don't get 0, that means no such self-consistent Hartree-Fock solution exists. So this provides a simple algorithm where we can say, you give me some candidate platform like 5-layer, multi-layer graphene, and you guess at the Chern number, and you see whether this equation is satisfied. And if it's satisfied, then that means Hartree-Fock can open a gap to give us a Chern band with the Chern number that you guessed in the first place. These form factors are a little bit complicated. I shouldn't have even written them here. The only point of writing them is just to show what goes into them. So you have to guess at the Chern number. So the Chern number enters. And then these things are just the form factors. So they look complicated, but they're something that can be very easily computed. And that's the only point of showing them here. So now I want to spend the last 5 minutes to apply this to the rhombohedral graphene example. So we're going to do 2 different things. First, we're going to ignore interactions, and that's like the first thing that I talked about. And then we're going to turn off so that would be when the potential comes purely from HBN. Then we're going to turn off the HBN potential and consider the anomalous case. And then we're going to combine those. So the first case is we ignore interactions. So we say, suppose that we have a potential which is coming from HBN sitting on 5 layers of graphene. Then we go back to that little table that I showed. It had these colorful pictures on it. We compute these form factors, and we see where we lie in this phase diagram, and we get the following result. So this would be 5 layers of graphene, 6 layers, 7 layers of graphene. And the x-axis is the displacement field, and the y-axis is the Chern number. And so we see that we can actually get Chern bands through this procedure. But the problem is that these Chern bands are not isolated. So the second plot is showing the gap to the Chern band. And the gap, as we increase the displacement field, gets very small. It's small for the reason that was said in the last talk, because as we increase the displacement field, the potential is being pushed away from the layer where the electrons are. The electrons are being pushed away from the layer where the potential is. And so, yeah, you can actually get a Chern band, but it won't be gapped from the other bands. And this seems inconsistent with the experiment. How can you measure a quantized anomalous Hall effect if your gap is very small? So we conclude from this that probably a completely non-interacting model is not the way that we get these topological flat bands here. Okay, so then let's look at the other limit. The other limit is we completely ignore the potential from HBN, and we only look at the Hartree-Fock interactions. So we only need to look at one equation, and this has a lot of stuff packed into it, but we just check for Chern number 0, 1, 2, any values of Chern number that we are interested in, does this have a self-consistent solution? And so now, again, we did this for 5, 6, and 7 layers. We see that all of these layers, so the x-axis is displacement field, y-axis is the Chern number, all of these have the same Chern number now. And if we look at the gap as a function of displacement field, we see that the gap is non-vanishing. And it stays non-vanishing even as the displacement field is turned up. And so we interpret this result as saying that at large displacement field, the Chern number is interaction driven. Of course, this is already known from the original papers on this work, but we can get kind of, this is a simple story that tells us why, and it can be extended to other materials, to other candidate materials, like, for example, looking at any number of layers in the multi-layer graphene. And we can combine these things. We can combine the case of no interactions and all interactions and get some result that's probably more relevant for the experiment. One of the other advantages of this kind of simple model is that we can also try to gain some intuition about this. And so, so we looked at the Hartree and the Fock terms separately, and this is actually looking at 3 layers through 8 layers. And so let me just tell you what these plots mean, because they're a little bit weird. I'm showing where the K point in the mini Brillouin zone is sitting. So as I change the periodicity, then I'll change where the K point is. I have a superlattice with a periodicity, it gives me a K point. So as I change that superlattice periodicity, I'll change where the K point lies. And so that would be the kappa X or kappa Y coordinate. And so having HBN on graphene fixes where the K point is if they're perfectly aligned, and that's what this first cross indicates. And if I start twisting HBN, then I start moving around where the K point lies. And so that's what these little crosses are showing me. Where's the K point in here? And so the colored regions are showing me the Chern number for these different situations of HBN twisted on multi-layer graphene. And so what we can see here is that if there's no twist at all, then we're in this white region, which is metallic. It doesn't predict we don't predict any Chern number here. It actually requires a finite amount of twist to get into this blue region that has a Chern number -1, consistent with experiment and consistent with previous results. And then if you twisted it further, then you can get into some other regions. So I think one of the new outputs that comes out of this simple calculation is that it actually requires a finite amount of twist in this aligned system in order to realize the Chern 1 band in this experiment. The other thing that was already known is that it actually requires interactions to realize this Chern band. And then what we see here by splitting up the Hartree and the Fock contributions is that the Hartree contribution is only giving you metal, and the Chern band is coming entirely from the Fock contribution. And the way that we can understand this is because the Fock contribution is the one which is calculating, including all of the Berry phase. And so we have a way of estimating what is the critical value, what's the critical value of, say, twist angle that you need in order to realize this Chern 1 band, which is to say, what's the critical amount of Berry curvature that you need to include to get a Chern 1 band. And that allows us to estimate where you switch from this white region, which is metallic, into this blue region, which has a finite Chern number. Okay, and the other thing that we can draw from this plot is actually kind of interesting. So 5, 6, 7, 8 layers, they all have the potential to realize this churn 1 band. We don't see it at 4 layers. What's different? Well, actually, you would see this blue region, but it's outside of the single band regime. And so this is kind of an interesting prediction where in the experiments, the churn 1 band has been observed for 5 and for 6 layers, but not for 4 layers. And this might provide some intuition for that. Okay, so, right, so the last point that I want to make is what I said. We can actually estimate where the transition will be based on the amount of Berry curvature enclosed in the continuum model. So just to summarize the main points, the main point is that if we want to predict new materials that will realize topological flat bands in the presence of a superlattice, we developed a simple heuristic for doing that. The input data is, say, Berry curvature. The output is churn number. And this applies not only in the single particle picture, but also in the case of Hartree-Fock interactions. We applied it to bilayer and multi-layer graphene, but those results are already known. And so what we need to think of, and what I'd love to discuss with people, is are there some other 2D materials that you're thinking of where we could apply this algorithm to? And I'll end there. Thanks for your attention.
So, great talk, actually. So I have a comment and a question. So the comment is that, and this, you know, I'm sure people on the other side of the aisle would agree, that when you have, whether Moiré is important or not, of course, a single particle level is in the wave functions, but at an interacting level, it has to do with how you do the subtraction of the background. And this is something that Reddy and Fu pointed out through a phenomenological term in Long's paper.
Oh, yeah,
So if you take the interactions, it's pretty clear that at V equals to 0, a small displacement field, the interaction scheme of just projecting to the conduction bands cannot be correct. So the question is, whether this is correct at finite field? That was just a comment. Now, the question is, if I look back onto your plot of the churn number, and this is related to Ashwin's answer to my question before, I don't see any churn number 0 on that, right? It's always, you always get, at the filling that Long has in his paper, you always get a churn number non-zero, right? Is that true?
Yeah, so maybe it's actually better to look at this kind of plot. Yeah, so this is, at the filling, so this is actually using, using data from his paper, trying to use data from his paper. So we see that we have churn number 1, the twist angle there I think is around like 0.7 degrees or so, so that's in this blue. But we fixed,
but
easy, so I need to look at the other
I'm just
plot.
asking, but you have it, you have the plot there over E field, right? So as a function of E field going from 0 to large, there's no region of churn number 0.
So, right, so, if I only consider interactions, that's correct.
Okay, so I'm just trying to understand whether this is a feature that can be changed by other parameters or not.
Well, maybe
and if it can be changed by other parameters, can we see
can I just say, let me say one thing about that, which is, so the first case is considering no interactions. What that means is that, small gaps, but that's coming from, in the case of small displacement field, then that is the regime that might be relevant.
Why? There is interactions in the case of small.
Right. So no, it's no interactions means that the Moiré potential is creating the HBN is creating the potential.
Even for there would be interaction in the small field limit. There's still interactions. You just have to normalize.
Sure. These are just the data. So let me just say, the real system is combining these two rows. But I'm considering 2 limiting cases. And so I can get a churn number of 0, which is like this little region here, in the situation where I have no interactions and the potential is coming from, the HBM potential is important. That's actually what's making this.
Even that equals 0.
Sure. So what I'm trying to say is that if I combine the first row and the first row shows me a place where I can get a churn 0. The second row, Well, what no interactions means here, what it means is that the HBN potential is important. And so if that potential is important, then it could be more important than that induced by interactions. So I need to combine them with some weighting factor. And so that's why I'm saying it's conceivable that they can be combined and create a Chern zero.
Then we're probably doing just some sort of different background subtraction.
Yeah, possibly. I mean, also there's some unknown weighting factor, which again, if you're going to go through the trouble of doing that correctly, then it's outside the scope of this idea.
I had a question about this n equal to 4 thing you mentioned. Is that, you said there's no Chern 1, is that for that particular displacement field?
Yes, right. So,
okay.
So this is, well, I don't know that, I don't remember how many values of this displacement field we checked, but I think we were in the large field, like around in checking values of finite field here.
Because most calculations give you a Chern band for n equal to 4, but you have to go to higher displacement fields, and I think Long sees that in the experiment as well. So the comment that's not there is
not
for
a
the
correct comment.
Well, or it's for lower displacement field, maybe.
Yeah, so let me, what I didn't say is what this hatched region means. So for us, we want to consider a single band limit. And so that's the region where when you apply the displacement field, you have, you're at a filling where where you don't need to consider the next higher band. Or I should say, basically the mini Brillouin zone is such that you're not ever looking at the next higher band. And so it gets cut out from this calculation. And so I think for us, it might be sitting in this hatched region. Yeah. Possibly. That's my out. Yeah. Okay.
Thank you very much for this very nice talk. So I have a question whether you can use now, because you have now a scheme to really check what is happening. Can you use that as an inverted design? So that means that you can now define what kind of system the experimentalists could try, where you find really what you would like to have.
Yeah, so I think that the obvious answer is you want a high concentration of Berry curvature. And I think everyone knew that going in. I think maybe the more interesting case is that result is that result is in this kind of very long period limit. But if maybe you're not in that limit, and maybe then you could engineer something with the form factors. So it would actually be more interesting if you had, say, a Chern zero band that somehow had a lot of, had a lot of non-trivial band mixing, but didn't somehow have a concentration of Berry curvature. That would be a more kind of unusual situation that we could think about. I think the problem is that most of the 2D materials that we know are graphene-based, and so we weren't too motivated to try to construct some exotic example. Yeah.
Okay.
Yeah.
Thank you.
Hi, thank you. So I just wanted to double check the understanding. If I don't have a superlattice and I consider the Berry curvature, can I just draw a superlattice Brillouin zone and add up the Berry curvature there, and that'll
that's exactly what we're saying. That to an approximation, yes, it's the amount of Berry curvature enclosed in the Brillouin zone.
Regardless of how strong the superlattice potential is?
Right, except this is a perturbative result, and so the superlattice potential has to be weak enough that that kind of degenerate perturbation theory is the right way to solve the problem.
Gotcha.
Yeah, that's the claim.
Thanks for the nice talk, Jen. I was just wondering, so in this case, like the Chern numbers that you determine are modulo some integers, right?
Yes.
So could you look at the Berry curvature and then say like which, like whether it's Chern 1 or Chern 4, for example, for a C3 symmetric system, or that's not doable within your approximation scheme?
Yeah, I think that's probably not doable from this scheme. That's a cool question to ask. I guess what you could do is you could try to, you could look for places where like a gap closes, and if your Chern number is kind of staying, then you could kind of track how it jumps. But no, I don't think we can get that since we're really relying on the symmetry indicator formulas. Yeah.
So TrackUp had this model where I thought the main take home from that was that this idea of chopping Berry curvature doesn't always work. In particular, when you have a potential, the Chern number you get is opposite of the Berry curvature you put in. Does this show up here, or would that be kind of a case where this method doesn't work?
So I don't know how that model, I don't know the details of that model. Maybe you can say a little bit more about it, but this is true as long as your superlattice is perturbative. And so it might be that his model is relying on mixing the first and second band, and then this will break down. Yeah. Yeah.
Okay, yeah.
You do have a minus sign.
Yeah.
So yeah, yeah.
Yeah, I'm not sure what. So this is our table, and I don't know if this.
Yeah, so I think that your approach can definitely capture this effect, and it might be in like you see pi minus phi b over 2 pi in the middle right there. So I guess is phi b is like the total integrated Berry flux, and sort of the Chern number enters with the minus sign.
Yeah, but as you can, right, so this is Berry flux. It's, it's not the Chern number of the band. If the phi b is small, then this will still round down, whether it's a positive or negative amount. Yeah.
I mean, that's all I'm saying. And I think it's probably opposite for when you consider the Hartree-Fock, the interaction case.
Yeah, so the Fock term usually enters with a minus sign. I don't know what model we're talking about, so it's hard for me to answer the question.
Yeah, we can chat afterwards.
Yeah.
But sorry,
yeah.
Because it's defined mod 3, so 1 is minus 2. Right.
Yeah.
That could be the resolution also, yeah. I don't know.
Keep that one offline. Any other questions? Let's thank Jen again.